Hi everyone. Today we're going to continue our discussion on nuclear chemistry. So first, we're going to talk about isotope half-life. So remember that isotopes that are unstable go through either alpha decay or beta decay or maybe positron emission or electron capture. And during that process, the isotope is converted into an isotope of a different element. So over time, a sample of a radioactive element is going to decrease in amount. So the half-life of an isotope is the time required for 1/2 of the unstable nuclei to undergo radioactive decay. So as an example, let's say we have uranium-238. And let's say that we have 100 of these uranium-238 isotopes. Now, the half-life of uranium-238 is really long. It takes many, many, many years for this sample to decay. So let's say that we wait long enough. Well, this would be outside of our lifespan. But let's say, we were able to record over time the amount of the sample left. So let's say at some point we find that only 50 isotopes are left in our sample. So that's half of the amount that we started with. How long did that take? Well, if we can track the time it took for that to occur, that would be our half-life. So down below we have a graph where on the y-axis we have the fraction of sample remaining, and then the number of half-lives elapsed is on the x-axis. So let's say one half-life has occurred, so maybe that's 1 billion years. So we wait 1 billion years and only half of the sample remains. So now let's say we wait another 1 billion years. So a second half-life has elapsed. Only 1/4 of the sample will be left over. So in our example above, only 25 isotopes will be left. And we can keep going. Now, the half-life of an isotope, so the time it takes to lose half of our sample, is used to indicate stability. So the longer the half-life, the more stable the isotope. So in your textbook, there's a table, table 10.2, and this just gives some examples of half-lives. So for instance, uranium-238, which is shown first, that has a half-life of 4.5 times 10 to the 9th years. Wow, that's a super long time. So yeah, we wouldn't even be alive after half the sample disappeared. Now, if we go down the list, you'll notice that carbon-14, its half-life is 5,600 years. Now, carbon-14 is actually a really important isotope. We'll talk about later why that is. Now, if we keep going down the list, we start getting into synthetically produced isotopes. And you'll notice that their half-lives are quite small by comparison, at least for most of them. So for instance, oxygen-15, its half-life is only 2 minutes. So it doesn't last very long, and that's partially why it's synthetically produced, because it just doesn't exist in nature. So again, the length of the half-life determines stability. So uranium-238 at the top, its half-life is super large, so that means it's pretty stable. It's still radioactive, but it's relatively stable. And then carbon-14, its half-life is 5,600 years, so it's less stable than uranium. And then oxygen-15 is super unstable. Its half-life is only 2 minutes. So let's do an example calculation. where we try to determine the half-life of an isotope. So iodine 132 decays by beta emission and forms xenon gas. So that would actually look like, let's see, 132, and its atomic number is 53. I looked it up earlier. And then it will, go through beta decay, and remember a beta particle is the same as an electron, and it will form xenon 132, but the atomic number of xenon is 54. So you'll notice that the mass numbers add up on both sides to 132, and the atomic numbers add up on both sides to 53. So everything is balanced. Now, that's not what's important in this particular problem. In this particular problem, we start with 100 milligrams of solid iodine 132, and then it has a mass of 12.5 milligrams after decaying for 6.9 hours. So we're going to assume that the xenon gas formed by the decay all escapes into the air. So it's not contributing to the mass of iodine 132. So let's determine the half-life of iodine 132. Okay, so if we start with 100 milligrams, how much would we have after 1/2 of it disappears? We would have 50 milligrams. Okay, so now what if another half-life passes by? What's half of 50? 25. Okay, so now let's say another half-life passes by. How much is left over? 12.5 milligrams. Okay, so what this tells us is we've gone through 3 total half-lives. So the first arrow represents the first half-life, the second arrow is the second half-life, third arrow is the third half-life. And we don't know how much time that is yet, but we're going to try to solve for it. Okay, so we've gone through 3 half-lives. So now let's take the time it took for the sample to decay that much, and we're going to divide that by 3. So we're going to take that 6.9 hours and divide it by 3, and then that will give us how much time the half-life is equal to. So let's see, 6.9 divided by 3. All right, so we get 2.3 hours. That is our half-life. So it's not too bad. We're just using what we know about half-lives. So the fact that half the sample disappears each time. And then we're using the total time it took to get from 100 milligrams to 12.5 milligrams and the number of half-lives to determine how many hours passed in between each amount. Okay. And here's the solution slide. It's all in words, so it might not be quite as useful, but I didn't have a good way to represent it. Now for the next example. After decaying for 60 hours, only 1/16 of the original sample of a radioactive isotope remains. What is the half-life of the isotope? Okay, so let's see. So we're assuming that maybe we started with a fraction of 1. And then we know that after 1 half-life, we have 1/2 of our original sample. And then after another half-life, we have 1/4. And then after another half-life, we have, let's see, 1/4 divided by 2. Dun, 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 that would be 1/8. And then we have one more half-life, and that gets us to 1/16. So this is really similar to that graph I showed you earlier. So on the y-axis, we started out with 1 as our fraction, and after one half-life, we had 1/2 of our sample left. And then after another half-life, we had 1/4 of the sample left, and so on and so forth. So it's kind of a similar idea there. Okay, so this tells me that this sample underwent 4 half-lives. There were 4 arrows there. So now let's figure out what the half-life of the isotope is. So we're going to take the total time it took for this to occur, which was 80 hours, and divide it by 4. All right, so that should give us 20 hours, and that is the half-life. So again, we're not doing anything too fancy. We're just kind of figuring out, okay, if we only have 1/16 of the sample left, well, assuming we started with a fraction of 1, how many half-lives have we gone through? Or how many half-lives have occurred? Once we know the number of half-lives, we can just divide the total time it took by that number to get the half-life. So it takes 20 hours for this particular radioactive isotope to decay to half of its original sample size. All right, and here's an explanation of that calculation. All right, so now let's talk about the health effects of radiation from nuclear reactions. So the greatest danger to living organisms of exposure to long-term, low-level radiation is the ability of high-energy or ionizing radiation to dislodge electrons from molecules and generate highly reactive particles called radicals or free radicals. So let's say that something goes through alpha decay. So it produces an alpha particle. That alpha particle has a lot of energy. So if, let's say, we ingest that alpha particle, it could interact with atoms in our body and ionize them. So that means that if we have, let's say, an atom, it's going to, let's say this is our alpha particle down here, it could hit this atom, and the atom will release an electron. So then that atom becomes positively charged. Now this could have disastrous effects on our cells or other biological molecules. Now additionally, this might produce something called a free radical. So a free radical is something that has one single electron just hanging out, and it's not paired up. So, for example, maybe we have an oxygen atom, and we'll draw a Lewis symbol here. Maybe it just has a single electron just hanging out on the side, which is unusual for oxygen. So free radicals are very reactive because, again, they have that one electron that really wants to pair up with something else. So that makes it really unstable. So these free radicals could cause reactions to occur among stable materials in the cells of organisms, such as genes and chromosomes. And those reactions might lead to genetic mutations, cancer, or other serious conditions. So in fact, free radicals in the atmosphere can be absorbed into our skin, for instance, and that could have effects on the health of our skin. I think there's actually lotions out there that say they can block free radicals from the environment. Now, short-term exposure to intense radiation, so let's say you go near the site of a nuclear disaster or something, that will result in tissue destruction in the exposed area, and that can cause symptoms of acute radiation syndrome. So you might feel really sick or ill. You might experience nausea or vomiting. So radiation can be very damaging. Now, earlier I talked about how we can stop radiation or block it. So remember, alpha particles are quite massive, so they can be stopped pretty easily by something like a sheet of paper. However, if we ingest alpha particles, that's when the possible biological destruction occurs. Beta particles are smaller than alpha particles, so remember they need something a bit thicker to stop them, or else the beta particles will just pass right through. So we need something like lead or concrete. And same for gamma rays. Remember, gamma rays aren't really particles, they're a form of waves. And so they can pass through things really easily. So again, you need something super thick like lead or concrete. Now, how do we detect that we've been exposed to radiation? So most often, if workers are near a site of possible radiation, they'll wear film badges, and those film badges will develop if they're exposed to radiation. So the degree of exposure will indicate the radiation dose that the person has been absorbed or exposed to during that time. Another way to detect radiation is using what are called Geiger-Müller tubes. So these are devices that operate on the principle that ions form when radiation passes through a tube filled with a low-pressure gas. So there's actually a figure on the next slide showing how Geiger-Müller tubes work. So I actually went to a high school that was built at around the beginning of the Cold War with Russia. And apparently there was a bunker in my high school that nobody knew about. And the school was kind of cleaning out some of the closets in the basement. And they found a Geiger-Müller tube. Because back then, the US was scared that they would be attacked with nuclear weapons. So they wanted a way to detect radiation. Now, a Geiger-Müller tube is shown up above, and it has this tube off to the side, and then it also has a meter on it. And basically in that tube is argon gas or a similar gas, and the argon gas can be ionized by radioactive elements and their decay products. So for instance, if we have an argon atom, remember argon has an even number of electrons. It has 18 electrons. But if it's hit with a really high energy alpha particle, for instance, argon might lose an electron and become positively charged as a result. Now, the electrons that are produced from this interaction will hit something called an anode in the middle, which is positively charged. That's right here. And you'll hear a click every time that occurs. So the Geiger-Müller tube makes this like click, click, click sound every time an electron hits that anode. And so that's how you can tell if there's, radiation nearby. Now, there's always some background radiation that occurs because, again, there are natural radioactive isotopes around us, which is perfectly fine. It's, not going to harm us too much. But if you're in an area with a lot of radiation, suddenly you'll hear a bunch of clicks happening. And then the meter on the Geiger-Müller tube will also indicate the level of radiation. Okay, so there are some medical uses of radioactive elements. So they're not all bad. We can utilize them for good. So radioactive isotopes can be detected easily in the body by using radiation detectors. So we want to use radioactive isotopes and radioactive isotopes that mimic non-radioactive isotopes. Because radioactive isotopes will then go through the same chemical reactions in the body. However, because those radioactive isotopes are giving off, let's say, beta particles or gamma rays, we can detect where that's occurring in the body. So we actually call radioactive isotopes tracers in diagnostic medical work, and they can also be used as therapeutic agents in some medical treatments. So again, tracers are radioisotopes or radioactive elements that are used medically because their progress through the body or their localization in specific organs can be readily followed. Now, there are 5 characteristics that we want to follow before we use a radioisotope on a patient. So tracers should have short half-lives, so they will decay quickly, but we also want them to give off as little radiation as possible after the procedure is completed. And then the daughter nuclide that's produced by the decaying tracer should be non-toxic, and that should give off little or no radiation of its own. So ideally, the products would be stable. Also, the tracer should have a long enough half-life to allow it to be prepared and administered conveniently. So there's kind of this battle of, well, we don't want it to decay too quickly or else we can't detect it or even give it to the patient, but we don't want it to decay over too long a period of time because then it will just sit in that person's body and potentially cause damage. So if possible, the radiation given off by the tracer should be gamma rays because they penetrate tissue well and can be detected readily. Additionally, the tracer should have chemical properties that make it possible for the tissue being studied to either concentrate it in diseased areas and form a hotspot, or reject it from diseased areas and form a cold spot. So, for instance, maybe you go to the doctor and they give you something that's radioactive, so it has a tracer in it, and maybe it collects at a very specific point in your body based on, different interactions. So maybe you have appendicitis, but you're not sure. They can use tracers which will all congregate near your appendix if it's infected, for instance. And then you can detect where those tracers went. If you have appendicitis, the tracers will show up near your appendix. If you don't, they won't congregate there or concentrate there. So down below is something called a positron emission tomography scan, or a PET scan. And this is of someone's brain, and you can see that there are some clear colors showing up in this scan. So those colors are due to radioactive elements or tracers, and in particular, they use fluorine 18 for PET scans. So some other medically useful radioisotopes are shown in Table 10.6. So for instance, phosphorus 32. This has a half-life of 14.3 days, so that's pretty short. And this is used in the detection of tumors and the treatment of a particular form of leukemia. Let's see, there's also cobalt-60, which has a half-life of 5.3 years. So that's a bit longer, but it is used in cancer treatment. Strontium-85 is used to in bone scans for diagnosis. And then iodine-123 is used to diagnose thyroid cancer. And also in the treatment, iodine-131 is what's used in the treatment of thyroid cancer. And so there are a lot of different tracers we can use in medicine. So even though radioactive elements can be dangerous, we can use them to help people. So one more useful thing we can do is use carbon-14, which I mentioned earlier, to help us figure out how old objects are. So maybe we find a fossil and we want to figure out how old the fossil is. Maybe we find an old manuscript and we want to figure out, how old is this manuscript? So carbon dating is really cool and really useful. All right, so what is shown down below is a cartoon of how carbon dating works. So cosmic rays from the sun actually will collide with atoms in the upper atmosphere, and that will produce energetic neutrons. And then those neutrons will collide with nitrogen-14 isotopes to produce carbon-14 and a proton. Now, carbon-14 is not very abundant in nature. The most abundant isotope of carbon is carbon-12. So carbon-14 is not found very often in nature. However, it's found enough that we can use it to figure out how old something is. So what ends up happening is carbon-14 will oxidize and turn into carbon dioxide. But the carbon has a greater mass than carbon-12. So then carbon dioxide will float down to the lower atmosphere and it will be absorbed by different plants during photosynthesis. And then, of course, animals or humans will eat those plants and they are ingesting carbon-14. Now, again, it sounds scary that we're ingesting a radioactive element, right? But remember, this is present in a really small amount, and it's really not that dangerous. There are naturally occurring radioactive elements all around us, and it's a low enough amount that we're safe and we're fine. Now, what ends up happening is, let's say this poor cow here who ingested some plants, let's say he dies, unfortunately. And what we can do is look at, okay, what is the carbon-14 to carbon-12 ratio when that cow dies? So remember, if the cow isn't ingesting plants anymore because it died, its carbon-14 amount will just decrease over time. It's not going to be replenished anymore. So carbon-14 is going to decay because it's radioactive, and we can compare the ratio of carbon-14 to carbon-12 from the cow to a healthy animal that's still alive and figure out, okay, how long has this cow been dead? So we can also do that with plants like trees. If we chop down a tree, we could use carbon dating to figure out how old is this tree. or when did it die? And so carbon dating is a really cool method to figure out how old something is. And that is actually the end of the lecture. So that's the end of our course. So if you have any questions or you need any help with some last minute assignments, just let me know. It's been a super great quarter. You guys have been awesome having to deal with all of the craziness of learning online. I'm sure it was really stressful and overwhelming at times, but you did it. So good job. And I hope you all have a wonderful summer and good luck on the final exam. Hopefully I'll see you all in person soon.